Hello and good day, everyone. This is a group project for KM30903 for mechanical design. And today we're going to talk about motorization of a traditional wheelchair. Okay, so for our team, it consists of me, Allan, Wilson Lo Wishong, RANDALL DYER SARUYAN, and also JC DARREN MOJIUN. Okay, so for introduction, what is a motorized traditional wheelchair? It is a mobility aids that utilizes electric motors, which designed for individuals that are unable to propel a manual wheelchair due to physical limitations. So why and how is it beneficial? It is for those with cardiovascular issues, fatigue-related problems, and conventional mobility difficulties. Okay, so what are the types of electric-powered wheelchairs or EPW? Number one, hands-free operation, which use EMG, EEG, or EOG. Second one, front wheel powered chair, which is our project. And then rear wheel electrical powered wheelchair. So how future-proof would it be? So number one, it is a development of control algorithms and sensor integration to enhance usability and safety. Second, sensors used include sonar, infrared, ultrasonic, and gyroscopic for obstacle detection and navigation.
Hello there, my name is DARREN and I will be presenting on the objective. These are the few points for our project, our product, which is ensure the ease of operation and promotes user independence, designing hand bike attachment to be lightweight and detachable, to ensure that it is easy to install or remove, providing convenience and versatility for users, to foster a sense of autonomy and reduce reliance on caregivers, implementing a stable attachment mechanism for secure use, and include responsive throttle control and built-in braking system to enhance the user safety. So, what are the impact for our product? For me, I would say there are three impacts for this product, which is to make a motorized mobility accessible to more users and to provide an affordable upgrade path for existing wheelchair users for the traditional wheelchair. And for the last point is that to empower users through enhanced independence, meaning that, as you can see from the fifth objective, that we reduce the reliance on caregivers, and also the first point, which is to promote user independence. You don't need anyone to help you in a way to guide you, so that you could be on your own and everything's going to be fine. But apart from that, to ensure that it is easy to install and remove, meaning that we have that key features where it is lightweight and also detachable design for easy installation and actually for transportation, because for daily life of usage, you wheelchair are used in everywhere. For example, maybe a person with maybe the handicapped person is actually driving, but he needs to be able to put the wheelchair in, probably inside his car, to be transport to use in another places. But personally, and for our group, we discussed that actually the main reason for our project is that to improve the independence, meaning that you don't rely on anyone else to help you, and also giving you a sense that you are, in a way, using a modernized tech wheelchair who might you feel like, or you might be out of touch with technology and stuff. And also, our our product is that we focus also in a cost effective solution, which means that we transform existing manual wheelchairs into motorized ones using, like, as said before, a hand bike attachment, and avoiding the need for expensive and fully motorized wheelchair system.
Hello everyone, I'm Randall. So I'll walk you through the methodology for our project, which focuses on developing an affordable and portable electric towing system for wheelchair. Our approach is design based and structured into six key phases: conceptualization, design development, prototyping, performance testing, data analysis, and user feedback. Each phase is carefully planned to ensure that the final product meets the mobility needs of individuals with lower limb disabilities while remaining affordable and accessible. We begin with the conceptualization phase, which focuses on understanding the needs of our target. This involved reviewing existing literature on wheelchairs and mobility aids and identifying gaps in affordability and accessibility. To ensure real-world relevance, we also conducted interviews and surveys with potential users, gathering insights to inform the design. Next was the design development phase, where we created a 3D model of the towing system using SolidWorks. The design features include rotating joints for improved maneuverability and lightweight materials. Throughout this phase, iterative reviews and user feedback allows us to refine both functionality and aesthetics. In the prototyping phase, we built a working model based on the finalized design. The prototype was developed to meet rigorous safety and performance standards. We then conducted performance testing, evaluating the system under realistic conditions. Key criteria included supporting a user weight capacity of at least 80 kilograms, achieving a minimum range of 20 km per charge, navigating gradients of 1 to 12, ensuring effective braking within 10 meters. Then the testing was conducted in simulated environments and included user feedback to address usability and performance. So during the data analysis phase, we evaluated the performance metrics to ensure compliance with standards. We also perform a cost comparison with existing electric wheelchairs to demonstrate the economic viability for our system. These findings highlight the affordability and competitive edge of our design. Finally, in the user feedback phase, we distributed surveys to gather qualitative input from users. This feedback allows us to make refinements, enhancing usability and accessibility. Iterative testing cycles ensured that the system met the real-world needs of users effectively. In conclusion, this methodology provides a robust framework for developing an innovative and affordable mobility solution. Moving forward, we aim to expand sample sizes, explore real-world application, and even continue refining the design based on user feedback. Thank you.
Hello everyone, I'm Wilson. Now I'm going to talk about our result for our final product. As you can see, picture 1 is our prototype. How do we build it? We use a traditional wheelchair item such as bicycle handlebar, steel bar for welding, steel plate as platform, bicycle front fork, small all-terrain wheel which is bicycle wheel. We modify it ourselves. MY1016 which is a 24 volt DC motor, throttle for controlling the speed, Ion tag as our Arduino, Bosch battery, sprocket and chain. From the slides, we can see there's two red arrow there which is the point for connect it. We drill two holes and screw it into it, guarantee it will come off while we are using the prototype. So picture 1 is a normal bicycle handlebar. So we look towards picture 2. Picture 2 is the one we made it by welding it, extend it using steel bar, make it longer so it's suitable for our prototype. So picture 3 is showing our wiring using cable tie so it won't be messy. And besides we use heat shrink so it won't have short circuit. It don't have current flow if the wire was exposed to the metal or what. So picture 4 showing our Ion tag, which is our Arduino, and the battery placement. We put it near the motor so the wiring it won't be complicated. So for the last one, which is picture 5, which is the small all-terrain wheel, we using the bicycle wheel and sprocket, bicycle chain, and 24 volt DC motor. So we built a base for the DC motor and connect the chain to the sprocket so it will drive the wheels towards. Hello, now I'm going to talk about the result and analysis. So as you can see, there's two pictures in the slides. One is about 24-volt DC motor and one is about the graph of velocity against weight. So I'll talk about the 24-volt DC motor first. A distinct negative trend is observed where velocity decreases as weight increases. Velocity drops sharply from 14 km per hour at 55 kg to approximately 10 km per hour at 85 kg. The decline flattens slightly at higher weight, indicating a potential operational floor for velocity under load. So let's look on the graph of velocity against weight. We represent 55 kilogram as Allan, 65 for Randall, 80 for Jesse, and 95 for me. As you can see, the graph is slightly dropping from 55 kilogram until 95 kilogram. The results show that velocity of the motorized wheelchair decreases as weight increases.
Okay, so now we're going to talk about another analysis, which is the second graph, which is the graph of time against distance. So this is to show that the ability of the DC motor or the ability of the wheelchair itself. So this graph demonstrates a clear linear relationship showing that time increases proportionally with the distance across all the weights categories. So as you can see, we took data for 5 meter, 10 meter, 15 meter, and 20 meter, and then we record the time it take for completing the distance.
So, for the conclusion, this project successfully converted a standard manual wheelchair, which is a traditional wheelchair, into a motorized one, significantly enhancing the mobility and independence for individuals with disabilities. And also, as you can see, there are some technological advancements from this, which is we integrate a 250 watt process motor and durable lithium battery for extended usage cycles and eco-friendliness and superior performance. For the affordability, it utilizes cost-effective materials, which is we recycle metal. We don't even use, for example, a factory new metal. We use what we can and what is offered, and making it accessible to middle class families with potential for mass production. For also the future enhancement, we could incorporate voice gesture recognition, GPS tracking for safety and renewable energy, for example, like solar charging to improve functionality and sustainability. This initiative demonstrate a significant advancement in assistive technology, addressing mobility challenges while fostering independence and Inclusive inclusivity. Sorry. The project underscores how innovative engineering can positively impact the life of individuals with disability. So, from this conclusion, we deduced that our project is environmentally friendly design and it could improve the extended battery life if we could. And also for the accessibility breakthroughs, we are using a readily available materials, not for a cost effective stuff, and also that we want a middle classes people to be afford we could achieve that to afford them to in a way purchase this product. And also for the innovation that we could develop for our product is that we could have voice recognition integration plant, gesture control capabilities, GPS tracking for safety, and solar charging possibilities for renewable energy. And for societal impact, this is a major advancement in assistive technology, and we also enhance the quality of life for users, especially for those in handicapped and disabilities. We reduce the caregiver dependence, meaning that maybe a person is helping this disability, maybe the nurse, and we offer a greater mobility accessibility. So, from the objective, also, we could conclude that we achieve our objective for this product, which is for affordability and for improving the quality of life, basically. And also we could reduce the dependence, increase the independence, and also we innovate some technology to a traditionalized wheelchair in hopes that in a way we helped those who are in need, basically those with disabilities and handicapped. That is all from us. Thank you very much. And from me.
This is our design, as you can see. This goes in front of the wheelchair. So from the front, we have the handlebar, which is connected to the throttle, the Swiss, the starter, which is press fitted to a long bar, which is connected to the head and also the fork. So this is the wiring. This is the foot stand. This is a bar which is connected to the wheelchair. So as mentioned before, this is our motor. This is the chain which is connected to the sprocket and the wheel. And this is the placement for the battery and also our ion tech.
Hello. So this is our project, our prototype. This is the handlebar, like Allan said just now. It is press fitted into this long steel bar, and then from here you can see the welding point. We built a base for the motor, and the reason we place here is because it is easy for us to tilt. As you can see there, the wiring and the motor chain won't going anywhere or loose, because if we place here, it will affect the fork and the chain will loosen and get fell off. Let's see here. You guys see there's a 4 little hole on here. The reason we drill this hole is because after we install the wheelchair, and then we need to insert some screw to prevent it fell off or loosen while we using this prototype.
That's all for the working principle of this prototype. Now let's enjoy the demonstration.
Breakthrough! Ôi, tạm luôn à!